Hello, welcome to my ITCS presentation talk. I'll be presenting my paper Random Restrictions of Low Degree Bounded Polynomials or Juntas. If you want to find it on archive, the title is Aronson-Lamborghini's conjecture is true for random restrictions. So let's start. And I'll start by introducing the Aronson-Lamborghini's conjecture. So let's say we have a function from the Boolean hypercube to the bounded interval 0, 1. And the function is of low degree. The Aronson-Lamborghini's conjecture postulates a certain structural restriction about this function, which I am going to explain. Define the following two quantities. The variance of f is defined as the variance of the random variable f of x as we sample x uniformly at random from the input space. Now we define the influence of the ith coordinate as follows. Sample uniformly at random input x and flip its ith coordinate. See how much f changes when you flip the ith coordinate on expectation. So x superscript I means x with the ith coordinate flipped. This quantity is the influence of the ith coordinate because you can see it measures on average how much does f change when you flip the ith coordinate. And let's define the max influence to be the max influence. Aronson-Lamborghini's conjecture postulates that given a function such that its image of the Boolean hypercube is bounded, let's say within 0, 1, 1, and whose degree is at most b, you can lower bound the maximum influence in terms of its variance as follows. Now, this conjecture has significant consequences in quantum computing, particular the power of classical versus quantum query algorithms, which I'm going to explain in the next 2 minutes. But for now, all you need to know is that this is a very big conjecture. If you can prove this, you are probably going to get the Stocker-Fox space paper. And the consequence for, okay, before going into the, no, let's go into the consequences. So the consequence for this conjecture is the following. Let's say you have a quantum query algorithm which computes a function. So g is some function that you want to compute. Okay, g might not be a total function, g could be a partial function. So g is some function that you want to compute. And suppose you have a quantum query algorithm making q queries which computes g. So let's say q is a quantum query algorithm that makes at most q queries. Now the question is, can we simulate this classically? So in particular for every x, we can define the following function. P of x, the probability that q outputs 1 on input x. So the question is, can we estimate this probability P of x by a classical query algorithm that does not make too many more queries? And formally, we cannot expect this to do it for all x because otherwise we would have no classical two quantum separation. But can we do it for most x's or a large fraction of x's? So the question is, right bigger. Yeah, right bigger. So the question is, does there exist a classical query algorithm A which makes at most polynomially more queries than Q? Such that the L2 distance between Q and P, sorry, the L2 distance between A and P is not too large. Say at most 1 by 1000. And if in fact you can replace this 1 by 1000 by some arbitrarily small epsilon, and instead you would allow a factor of 1 by epsilon here. Anyway, if this conjecture is true, this means that given any quantum query algorithm, you can estimate its acceptance probability on most inputs by a classical query algorithm with small overhead. And this is an intuitive explanation for the fact that whenever we have a super polynomial separation between quantum query complexity and classical query complexity, it turns out that the set on which the function is defined, it's a partial function, the set is a very small fraction of the hypercube. Because if it was a large fraction of the hypercube, you could actually estimate it on most part of the points where it's defined. It's not a rigorous thing, but it's somewhat intuitively that's what it's saying. So anyway, this is the consequence of the Aronson-Dambanis conjecture on quantum query complexity. But even if you don't care too much about quantum query complexity, I think this conjecture is mathematically interesting in its own right. So I'm going to spend the next 5 minutes saying some trivial things about this conjecture. So we have a function. And it has a Fourier expansion, which is unique. Let's write it this way. And the degree of the function is simply the largest s for which the corresponding Fourier coefficient is non-zero. Now it turns out we can read out the variance and the influence of the function from its Fourier coefficients very nicely. Here is the formula for variance. And then it's the formula for influence. So to compute variance, you sum over the squares of Fourier coefficients of all the non-zero sets. And to compute the ith influence, you sum over the squares of the Fourier coefficients whose sets contain I. And from these two formulas, it's clear that the maximum influence is at least variance by n. But this is not what the Anson-Amani's conjecture asks. The Anson-Amani's conjecture asks us to lower bound the maximum influence in terms of a quantity that's independent of n. And that's the challenging part. And a priori, it's not even clear why such a bound should hold. Well, such a bound does hold for Boolean functions. This was proven by Bourgain in 2002. But for a long time, it remained unclear if such a bound should even hold. I mean, a bound independent of n should hold just for bounded functions. Well, such a bound does hold, and this was proven by a seminal paper of Dinur, Friedgart, Kindler, and O'Donnell. The reference will be linked in the description. They showed that max influence is lower bounded by a quantity independent of n and dependent just on the degree. But unfortunately, the dependence is inverse exponential. And the challenge here is replace 1 by 2 power t by 1 by t. Now, after it was formulated, this conjecture has garnered a lot of attention in recent years. I'm going to list some of the few works done on this conjecture. In 2002, Montanaro proved this conjecture for a special case of block multilinear forms. I am not going to write this on the blackboard, you can see this in the description. In 2022, Bansan, Silha, and Wolf proved this conjecture for the special case of completely bounded block multilinear forms. These are some specific polynomials which correspond to quantum query algorithms of a specific form. In 2016, O'Donnell and Zhao showed that it suffices to prove the conjecture for a specific class of functions called as one block decoupled polynomials. If you can do this for these specific functions, the general conjecture follows. In 2020, Keller and Klein claimed to find a proof for this conjecture, but unfortunately their proof had a fatal flaw and they retracted their paper. Later in 2019, earlier in 2019, Lovett and Zhang initiated a new line of attack using the notion of fractional block sensitivity. And this paper actually reproves one of their results using much more elementary techniques. So, coming to this result, what my paper shows is that if you take any function of low degree and which is bounded, and if you apply a random restriction of it with an appropriate restriction rate, with high probability, the Anson-Amani's conjecture will be true for this function. So, let f be a bounded function of degree t. Let rho be a random restriction, where every variable is kept alive with probability around order log d by d. For simplicity, let's also assume the variance of f is at least some small constant. This assumption can be removed with a bit more work, but with this assumption, it's simpler to state the statement. Now, what I show is that if you consider a random restriction with high probability, the answer Magnus conjecture will be true for the restricted function. In other words, the restricted function will have influential coordinate with high probability. By high, I mean non-negligible. It's not close to 1, but it's somewhat non-negligible. So this is the main result. And in the next 5 minutes, I'm going to give a sketch of how I prove this result. The starting point of the result is the paper of Dinur et al. Mentioned earlier, which states that if you have a bounded degree function, it can be approximated by a 2 power t Junta. It actually says something more. Let's take what it says. It says that if the Fourier tail above a level k is small enough, then the function can be approximated by a 2 power k Junta. Now we combine this result with the observation that random restrictions have decaying Fourier tails. So using some simple Carnot calculations, you can show that with high probability the Fourier tail of f rho beyond log d will be small. I am not showing the calculations here. So ideally, we would like to see the following. We do a random restriction of this rate, then the restricted function has small Fourier tail beyond level log d. Then we would try to use this result and say that therefore this function can be approximated by a 2 power log t, that is poly d Junta. And with high probability, since the variance of f was not too low, with some good probability, the variance of the restricted function will also be not too low. In which case, we can say that one of the coordinates of this Junta will have high influence. That is what we would have wanted. But unfortunately, the decay we get from Charnoff bound here is not as small as the decay they get there. So, if you ideally in their theorem, what we would like is that we replace k square log k by k. If we could do that, then these calculations would work out. After a random restriction, the Fourier mass beyond log d is small. It's small enough so that this theorem holds and we apply our result. But unfortunately, it's not that small. It's only exponential of minus order log d. And the theorem there needs a decay of around order k square log k. So, first approach. Can we try to improve this tail bound? Maybe they did some slack in their analysis. Maybe we can actually improve this minus k square log k to minus k, in which case we are done. But we cannot do that. The same paper constructs a function which says this tail bound is tight up to log k factors. And now what do we do? And this is the core technical part of this paper. We observed that this function is only talking about Fourier decay beyond level k. But the function itself could be of full degree, it could be of degree n. It turns out that the counterexample they construct to show that this is tight, the function they construct also has degree n. But here, we are working with random restrictions of a low degree function. So we have two facts that we can use. First, the Fourier tail beyond k is log d here. The Fourier tail beyond k is small. And second, the function itself is of low degree. Now, can we hope to improve this tail lower bound with the additional assumption that the Fourier mass beyond level d is exactly 0? It turns out we can, and this is the core technical part of this paper. And I'm going to write the main theorem next. So this is the main theorem of this lesson. Sorry, the main theorem of this paper. Sorry, I'm going to use a different notation for a particular reason. In this statement, capital C is a universal constant. So let's parse what we are saying. We are saying if H is a bounded degree D function and whose Fourier must be on level K is small, then H is epsilon close to a poly D and epsilon of order K Junta. And this helps us because in our setting of parameters, we will be setting K to be log D. And in this case, this quantity does become around, around exponential of minus order K, which is exactly what we wanted. And everything works out. So, to recap how we prove our main theorem, that is Aronson-Damiani's conjecture is true for a large fraction of random restrictions. We use some Charnoff form calculations to show that the random restriction has small Fourier tail beyond log d. Now, again to recap, ideally we would like to take k equals to log d in the DFKO statement and directly conclude that therefore the random restriction is close to a Junta. But we cannot do that because the Fourier tail lower bound here is not good enough. So instead what we do is that we observe that in addition to the fact that the Fourier mass beyond level k is small, if you take h to be f rho here, we have the fact that the degree of f rho itself is small. And using this extra fact, we improve this tail lower bound from this quantity to this quantity to this end up at setting of parameters where k equals to log t this quantity is exponential of minus of order k, which is exactly what we wanted, the parameters fit. So we do a random restriction, the Fourier tail drops. The Fourier tail drops, we use this theorem to show that the random restriction can be approximated by a Junta. Now, additionally, since the original function had some small, at least some small amount of variance, with good probability, the restricted function will also have a decent amount of variance. And that means that one of these approximating Juntas, approximating coordinates of this approximating Junta will be an influential coordinate. And that concludes the proof. And I'm not going into the technical details of this, but it's not very long. It's 4 or 5 pages, so it will take 1 hour to describe, and the limit is only 20 minutes. But you can read my paper if you are interested. I'll just say the fact that we need about bounded low degree functions that I used to put this. And this paper is discovered by a paper of Pilmas et al., which says the following. Let f be a bounded degree d function. The statement is the following. Take any input x. Take any partition of the coordinates, let's say into k coordinates. Now consider the following quantity. So I'm saying from x, flip the coordinates of sj, see how much f flips. Now sum this quantity over all these sj's. Note that sj's are mutually disjoint. This quantity is always bounded by a small number, order d square. The maximum of this quantity is called the block sensitivity of x. And Hilbert proved that this quantity is always bounded by a number that is just polynomially. So these sets are usually disjoint. And to improve this tail bound, I used this fact and the main idea of the DFTO paper, and it turns out they fit together in a very nice manner, and the parameters you get are exactly what you wanted. So this concludes my talk. Thank you for paying attention. I hope you enjoyed it.